Okay. Where am I? 21? X cubed plus 4 over x squared plus 4. All right, I notice we have polynomial. Over polynomial, the degree of the top is bigger than the bottom, so we're going to have to do long division first. Now, I'm going to put x cubed here plus 0x squared plus 0x plus 4. That way I give myself some room to write in the other pieces if I need them. X squared plus 4 here. So how do I turn x squared into x cubed? Multiply by x. X times x squared is x cubed. X times 4 is 4x. I'm going to put that right here. So I line it up in the x column. Come through, I change the signs. So here to here, get negative 4x. I cannot turn x squared into negative 4x, so that's my remainder. So I put plus my remainder over my divisor. So my integral now becomes integral this. X plus negative 4x over x squared plus 4 dx. And those I should be able to handle, especially that first one, right? I know that one. So let me just write this down. This is equal to 1/2 x squared, that's the antiderivative of x, minus 4 integral x over x squared plus 4 dx. So I just pulled the negative 4 out, created a new integral. This one I already took the antiderivative of. And so on this one right here, I realized that if I let u be the bottom, basic substitution, the derivative is 2x dx, which I almost have. I have x dx, so scale by 1/2. So that integral becomes integral 1 over u, and then the dx is going to be 1/2 du, so that's going to be 1/2 natural log of u plus a constant, 1/2 natural log of x squared plus 4. So I know that everything over here turns into 1/2 natural log of x squared plus 4 plus a constant. And then I had a negative 4 in front. So I have 1/2 x squared, the negative 4 times the 1/2 becomes a negative 2 natural log x squared plus 4 plus a constant. That's it. That one's pretty straightforward. All right, number 23. 10 over x minus 1 times x squared plus 9. All right, polynomial over polynomial. I do not need long division. And so I look at my factors. I have a distinct linear factor, and I have an irreducible quadratic factor. It's the first time we've seen this. So what I know is that this integrand has to be rewritten with an a over my distinct linear factor plus, now my irreducible quadratic factor here. But instead of b, anytime we have irreducible quadratic, we put bx plus c. So we put a linear expression on top of the quadratic expression if it's an irreducible quadratic, which it is in this case. And then I play the same game. I multiply both sides by the LCD. It cancels out over here, I get 10. Over here, I get the a. Then I get x squared plus 9. And then I get, this one's tricky. So let me write it down. I put x minus 1, x squared plus 9, x minus 1, x squared plus 9. Here the x minus 1's cancel, I get a times this. Here the x squared plus 9's cancel, I get bx plus c in parentheses times the x minus 1. And then now I don't think it's going to be impossible to kill off a. There's no way to make that 0. So I'm going to do the long method, distribute through. So here I just go here, here, ax squared plus 9a plus over here, bx squared, here to here, minus bx, here to here, plus cx, here to here, minus c. And now I'll collect all my like terms together. So 10 equals, here are my x terms right here. So I like x squared terms. I'd like to put them together one time here, a plus b, and then factor out the x squared. Then I'll do the x terms. There's one, there's one. So plus again, then in parentheses, negative b plus c times x. So I put those two together and I factored an x out. And then the things that don't have any numbers, or any x's, plus in parentheses 9a, and then it was minus c. And now I got to play this matching game. And again, over here, you don't have an x term, so 0x. You don't have an x squared term, so that. So I know a plus b must be 0. I know negative b plus c must be 0. And I know that 9a minus c must be 10. So I'm going to write this down in a system of equations. The first one, a plus b is 0. I'm going to write this, a plus b equals 0. Next one, negative b plus c, negative b plus c must be 0. Last one, 9a minus c must be 10. And then you can solve this using different methods. I'm going to use like an elimination sort of thing. First of all, let me add these two rows together because I notice I have a b and a negative b. So if I add those two rows together, I get a new equation, a plus c equals 0. Let me add these two rows together, and the c's will cancel, and I get 9a minus b, okay, 9a minus b equals 10. The original equation right here, a plus b, was equal to 0. Now you could use your calculator for this. I'm just doing it by hand. So I think these two right here are going to work. I can do this. This is like a little system, 2 equations, 2 unknowns. Add these straight down again. You get 10a equals 10, which means a is 1. Once I have a, I should be able to get everything else. Using this equation, if a is 1, you get 1 plus c is 0, which means c is negative 1. So now I know c, and then I can use this equation right here to get b. So negative b plus c, but c is negative 1, must be equal to 0. So negative b must be 1, which means b must be negative 1. So I know what a, b, and c are. All right, so now I come back over here. I rewrite the integral. And remember, this was the piece I was using right here. Right there. So this integral becomes integral, and then a over x minus 1. A was 1, so 1 over x minus 1. And then plus, here, bx plus c. So b is negative 1, so negative x plus c. C is negative 1 over x squared plus 9 dx. All right. Now, as bad as that might look, it's doable. The first piece of that integral is pretty straightforward. Natural log x minus 1. Plus, now the other part of this integral isn't very nice. I think what I'll do is these both have negatives, so I'm going to pull negative out and then pull it out here. And then I'm going to rewrite the integral, and I'll have, these will be positives. So x plus 1 over x squared plus 9 dx. All right, so at this point, I notice that I can split this into 2 integrals. I can do x over x squared plus 9, and then do it this way, plus 1 over x squared plus 9 dx. And this one I recognize, that's arctangent, right? The antiderivative arctangent. For this one, I need a basic substitution. I would just let u be x squared plus 9. du is 2x dx. I don't have 2x, I just have x, so 1/2 du is x dx. And so this integral right here would be integral 1/2 1 over u du, which would be 1/2 natural log u, which is 1/2 natural log x squared plus 9. So I know that this one right here is going to become 1/2 natural log x squared plus 9. This one's going to be arctangent, and then I have a negative in front. So I think I'm ready for my final answer here. Okay, so this is equal to, I had the natural log x minus 1 in front, then minus, okay, the antiderivative of this one we said was this, so 1/2 natural log x squared plus 9, and then this minus goes to this one also, so minus, and then this is arctangent. Remember, this is 3 squared, so a is 3, so we use the formula, it's 1 over a, 1 over 3, arctangent of, in this case, x over a, which was 3, and then plus c. And that's it. Check this one. What number was that? 23? Looking good, looking good. 25, my goodness, 25 looks like a monster. 10, 12, we'll probably go for another 20 minutes. X cubed plus x squared plus 2x plus 1 over x squared plus 1 times x squared plus 2 dx. Polynomial over polynomial. Degree of the numerator is 3. Degree of denominator, if we multiply these together, would be 4, because x squared times x squared is x to the 4th. So no long division necessary. Noticing my denominator has 2 factors in it. These are irreducible quadratics. Cannot factor these, right? So I'm going to be trying to rewrite this. Disaster. As my first irreducible quadratic with ax plus b, so that's a linear expression on top, plus my second irreducible quadratic with another linear expression on top. Now just think about what we're doing here. If we can get this to work out, I can split this into 2 integrals. And what I would have is ax over this, and I could do a basic u substitution, and I have b over this, which would be an arctan. Same thing here, exactly. So let's try and figure out what a, b, c, and d are. So I multiply both sides by the LCD. Everything cancels over here except for x cubed plus x squared plus 2x plus 1. The right side, when I multiply this one times this, the x squared plus 1's cancel, and I'm left with the ax plus b. But then that one factor that didn't cancel here was the x squared plus 2. Then plus, now when I multiply the LCD times this one, the x squared plus 2 factors cancel, but not the x squared plus 1. So I have cx plus d times the x squared plus 1. There's no way to kill off anything, so I've got to use the long method. I've got to multiply that all out. So this x cubed plus x squared plus 2x plus 1 must be, let's see, ax cubed plus 2ax plus bx squared plus 2b plus cx cubed plus cx plus dx squared plus d. Let's get like terms together. X cubes here and here, that's it. So I will have a plus c x cubed. Not x cubed, I wrote x squared. Okay, x squared terms. Here's an x squared, here's an x squared. So plus, in parentheses, b plus d x squared. All right, x terms. X, x. So plus 2a, that's here, and then the coefficient of that one is c with an x out there. And then last thing, I'm running out of symbols. 2b and d, so plus 2b plus d. Now that has to match, let me see, I got everything, yes. That has to match this side, x cubed plus x squared plus 2x plus 1. And so I match coefficients here. There's a 1 here, so that 1 must match up with this. The 1 in front here must match up with this. The 2 in front here must match up with this. And the 1 here must match up with this. So I'm going to have 4 equations, 4 unknown variables. So first one, a plus c is 1. A plus c is equal to 1. I'm giving myself enough room for a, b, c, and d here. The next one, b plus d, must be 1. The next one, 2a plus c must equal, let's see, 2a plus c must equal 2. And the last one, 2b plus d must be 1. All right, so what I do notice here is that these 2 equations right here both have a and c in them, so let me work with those. I have a plus c equals 1, and I have 2a plus c equals 2. So it's kind of like a new system. Again, you could use your calculator for this, but I'm just going through the work. So what I'll do is I'll multiply the top equation by -1. So I get a new system, negative a minus c equals -1. The second equation doesn't change. The reason I do that is because if I add straight down now, I get, this is an a, the c's cancel, and I get 1. So a is 1. All right, if I know what a is, then I can come in here and get c. So look at this equation right here. If I replace this with 1, I get 1 plus c equals 1. Subtract 1 from both sides. That means c is 0. So I know what a and c are. Similarly, these 2 equations both have b and d in them. So I'm going to do those over here. So this one, b plus d is equal to 1. The next one, 2b plus d is equal to 1. I'll do the same thing. I'll multiply the top one by -1, so it's going to change that to a negative, change that to a negative, change that to a negative. When I add down, I get b here. The d's cancel, and this is 0. And so if b is 0, then I can come into any of these equations, doesn't matter where, and find d. So I'll just do this one right here. That's 2 times 0, which is 0, and then plus d, so d must be equal to 1, 1. So I know what a, b, c, and d are here. So I'm ready to rewrite the original integral now. This is equal to integral had x squared plus 1, over here x squared plus 2, and it was ax plus b. So a is 1, so 1x plus b, but b is 0, so that's it. That's it. And then over here was cx plus d. So c is 0, so no x's, and d is 1, so it's just 1 right there. That's nice. That's real nice. Now, for this one, I make a basic u substitution. U is x squared plus 1, and then work through it. And you would get 1/2 natural log x squared plus 1. That's what you would get if you did the substitution. We've done that. This is the third time I've done something like that. And then this one is an arctangent. Recognizing that this is our a squared, so we actually have root 2 squared, that's 2, so a is root 2. So the formula is 1 over a arctangent of x over a plus c. So that should be it. I'll double check it. 25, 1 over root 2. Yep, okay. Let's see, I've got time maybe for one more. Let's see how bad this one is. 27. Oh, this is a good one. This is a real good one. 27. This is one that we got to do some magic. Do some magic. X plus 4 over x squared plus 2x plus 5 dx. Let me just double check I wrote that down right. Yep. All right, so here's the deal. You have polynomial over polynomial, don't need long division. You look at the bottom, you say, can I factor that? And it doesn't factor. So this is an irreducible quadratic. You cannot factor it. So if you go with the method says, okay, you're supposed to take this, x squared plus 2x plus 5, and I'm supposed to rewrite it as my irreducible quadratic with a linear expression on top, ax plus b. But think about that. You already have a linear expression on top. So if you did this, you would actually get back a is 1 and b is 4, and you'd be right back where you were. That doesn't help. And that's why I pointed out in class that when you have something like this, what you're going to do is, first of all, make a substitution of the entire denominator. And then take its derivative, which in this case would be 2x plus 2 dx. And then you look over here and you say, okay, look, if this is u, I would love for this to be du up here. I'd love for 2x plus 2 to match this exactly. But it doesn't. It doesn't. But this is where the magic is. We're going to make it happen. So first I'll start off. I need to make this a 2x. Or sorry, I need to make this a 2x to match with this 2x. But I can't just throw a 2 here. What I can do, though, is multiply 2 on the top and the bottom. And so now take the 2 just on top and distribute it through. And don't forget, distribute it through, right? 2x plus 8 over x squared plus 2x plus 5 dx. And then out here, since you slid the 2 on top, you still have the 2 on bottom, so it's like a 1/2. So that's the exact same problem. So you've got the 2x taken care of. Now you need a plus 2. So what I always recommend you do is right behind the 2x, you add a 0. And in this case, I wanted a plus 2, so the way I'm going to write that 0 is as follows. Here's the plus 2 that I wanted, but then minus 2. So that's 0. Then you still have plus 8 out there, right? Right here. All of this over x squared plus 2x plus 5 dx. And you may be looking at that going, okay, now what? Well, now what you can do, put these two together. That's a 6. And notice that you have 2x plus 2 here, right there. So if I just look at this over this, that's u and that's du. I have a perfect substitution to do there. This one, though, I still need to address. So this would become 1/2 integral. I'm going to split this into two completely different integrals. 2x plus 2 over x squared plus 2x plus 5 dx. That's one integral. Plus, now the 1/2 still, because the 1/2 had to go to both. Integral, now what was up here was a 6 over the irreducible quadratic. And what's the purpose? Why do it this way? Well, let's look at this. We already know this one is exactly du up top here, the bottom is u. So this really looks like the integral 1 over u du. That's what that integral is. And we know the antiderivative of that is natural log. We have a 1/2 out front, but we can take care of that. So let's do that. Let's actually take the antiderivative of that one right now. So the antiderivative of just this first one is 1/2 natural log of u, but u is the entire irreducible quadratic. All right, plus, now, this integral over here, I'm going to pull the 6 out, hits the 1/2, becomes a 3. Still have the integral because I haven't done the integral. And since I pulled the 6 out, I have a 1 up there. So I have 1 over x squared plus 2x plus 5 dx. Now, this is one of those preliminary concept problems that I said we need to know how to handle. If you have a constant on top of an irreducible quadratic, then the way to get it is to complete the square. So what I'm going to do is complete the square on this. So I take the number in front of x, which is positive 2. I divide it by 2, which gives me 1. Okay, that's my first important number. Then I take that 1 and I square it, which is also 1. That's my second important number. And so what I do now is I take x squared plus 2x. I take my second magic number and I add that 0, right? Add 1 minus 1. But I still had plus 5. These three guarantee to factor to be x and then this number, plus 1, and then squared. And then these two numbers right here give me a 4. And so this integral becomes 3 integral 1 over x plus 1 squared plus 4 dx. And does that look familiar? I hope so. Arctangent. All right, so if we make a quick substitution, u is x plus 1, du is dx. That integral, I'll even bring the 3 with me, is 1 over u squared plus 4 du. And so the antiderivative of this, 3 times, this is arctan with a being 2, so 1/2 arctangent of u over 2 plus a constant. But what was u? It was x plus 1. So here we go. Final answer. 1/2 natural log x squared plus 2x plus 5. I like this problem a lot. 3 times that, so it's 3/2 arctangent of u, but u is x plus 1, so x plus 1 over 2 plus c. That's it. That's all I have time for. Which number was this? 27. Beautiful. Okay, I gotta run.